Imagine you are given the task of distributing wires in the following village so that every house has access to electricity. One obvious way to solve this problem is to apply graph traversal algorithms like DFS or BFS to the input graph. Alternatively, you could also use the simple spanning tree algorithm we discussed earlier, which checks in every iteration whether adding an edge would create a cycle in the current subgraph. However, in the real world, distributing wires along a specific street is always associated with a certain cost. Therefore, the problem isn't just to find any arbitrary spanning tree in this graph. Instead, it involves finding a minimum spanning tree, a spanning tree where the sum of all edge weights is minimized. And you can probably imagine that there are many different spanning trees in this graph, and computing every single spanning tree to find the one with the minimum weight is probably not the most efficient approach. But don't worry, there are algorithms to solve this problem, and we will cover every single minimum spanning tree algorithm in this chapter. Chapter 4 is split into two videos. This one provides an overview over all minimum spanning tree algorithms and includes detailed explanations and implementations of the two most common ones, that is Kruskal and Prim. In the second video we looked then at an improvement of Kruskal's algorithm using the so-called union finds data structure. This data structure is also used then in Borufka's algorithm. Although the union finds data structure is based on a very simple idea, explaining it properly, especially its implementation, takes some time. For this reason, Chapter 4 has been split into two parts, Chapter 4.1 and Chapter 4.2. Now we will start with a general overview over all algorithms from this chapter, their creators and the order in which they were developed. The first minimum spanning tree algorithm was developed in 1926 and is known as Borufka's algorithm, named after the Czech mathematician Otakar Borufka. To understand the algorithm, we observe first that each node is its own connected component. Then we proceed by repeatedly connecting connected components using the cheapest edge. We start with the connected component that contains only the node 0. The cheapest edge to connect this connected component to another one has a weight of 4 and will be added to the spanning tree. Next we consider the connected component containing node 1. The cheapest edge to connect to another connected component has a weight of 4 and was already selected previously. Therefore we do nothing in this step. In the next step we select the connected component containing the node 2, select the smallest edge that connects to another connected component and continue in this way. Once we have processed all nodes, we notice that we have fewer connected components than at the beginning, and we have to repeat these steps over and over again until we have only one connected component. The next algorithm was developed in 1930 and is known as Prim's algorithm, named after the mathematician Robert Clay Prim. This algorithm requires a starting node, which can be interpreted as a tree. In the following steps, it continuously adds the cheapest edge to the tree that connects the tree to the rest of the graph. Prim's algorithm starts with a tree containing one node, whose size increases during the iterative process and which will never become disconnected as in Borufka's algorithm, or as in the next algorithm from 1956 known as Kruskal's algorithm, named after the mathematician Joseph Kruskal. Kruskal's algorithm starts by sorting all edges in the graph by their weights. Once this has been done, it proceeds by continuously adding the smallest edge to the subgraph that does not create a cycle. The cycle detection here can be executed using DFS or BFS, but it is much more efficient to use a union-find data structure for this purpose. Furthermore, there is another similar algorithm called Kruskal's reverse delete algorithm. This one starts also by sorting all edges by their weights, but now in decreasing order. Then it adds all edges to the graph that will form the spanning tree at the end and proceeds by continuously removing edges with the largest weights that do not disconnect the current graph. Now we start with a naive implementation of Kruskal's algorithm. To make things easier to understand, the algorithm will be applied to the following input graph, with weighted edges that are stored in a list. Here the function Kruskal has the input parameters V for the nodes and E for the list of edges including their weights. The first step within the algorithm is to initialize a list MST that will store all edges of the minimum spanning tree. Afterward, we sort the given list of edges in increasing order by their weights. Note that every edge in the input list must have 3 entries, the first 2 for the nodes connected to each other and 1 for the weight of the corresponding edge. The sorting algorithm used in this animation is insertion sort, which performs quite well on small lists and has the property of being a stable sorting algorithm. This means that it does not change the order of 2 elements with the same weight. However, one might consider using merge sort, quicksort or heap sort on larger lists due to their better time complexity. Once this has been done, we simply iterate through the sorted edges, starting with the edge that has the smallest weight. This edge will be added to the current spanning tree, and then we will check whether its inclusion in the spanning tree would lead to the creation of a cycle. If the cycle detection returns true, we must remove this edge from EMST, and otherwise it must remain in EMST. Furthermore, we check in every iteration whether the length of EMST is equal to the number of nodes minus 1. If this is the case, then the algorithm terminates. As mentioned before, this implementation is a very naive one that comes with a potential efficiency problem. Specifically, the issue arises in the line where we apply the cycle detection after appending an edge to our spanning tree. Here we might have to use a modified depth-first search in every iteration, which can cause high total costs, especially for large input graphs. But if you look closely at the execution of Kruskal's algorithm, you will see that there's actually a way to avoid the cycle detection. If we stop the animation here, we see a graph made up of many connected components, a subtree of the minimum spanning tree that will be returned at the end. The idea now is to assign each of these connected components to a specific group, for instance by using different colors. An edge is then selected only if it connects two nodes that do not belong to the same group, because if they did belong to the same group, adding the edge would obviously form a cycle. Otherwise, if an edge connects two nodes of two different groups, the groups are merged and the smaller group adopts the color of the larger one. And this is the idea behind Kruskal's algorithm using a union-finds data structure that we will consider in the second part of this chapter. Since Kruskal's algorithm builds its minimum spanning tree by selecting the smallest available edges from the graph as long as they don't create a cycle, the partial solution may be disconnected during the process. In contrast to that, Prim's algorithm starts with a single node and expands disconnected components step by continuously adding the smallest edge that connects the current component to a new node until all vertices of the graph are included. Furthermore, note that both algorithms may produce different minimum spanning trees if the underlying graph does not have distinct edge weights. Now, what is the idea behind an efficient implementation of Prim's algorithm? As explained before, Prim's algorithm starts with any arbitrary node in the graph. Then it considers a cut around the current connected component and looks for the edge with the lowest weight that connects this component to an undiscovered node. We will measure now the distance from our current subsolution to all other nodes. And this distance is simply defined as the weight of the cheapest edge connecting our current subsolution to any other node. All nodes that are not reachable from the current connected component via a single edge are assigned the distance of infinity. And since the goal is to always select the edge with the smallest weight that connects to an undiscovered node, we simply choose the edge to the node with the smallest distance value in each iteration. While the connected component continues to grow, we progressively move deeper into the graph and discover new nodes, which in turn let us update the distances to their neighboring nodes. Previously, our connected component consisted only of the nodes 0 and 1, and the cheapest edge connecting it, for instance, to node 4 had a weight of 94. But after adding node 5 to the component, a cheaper edge with weight 36 became available, so that we can update the distance value of node 4 accordingly to 36. Similarly, the distance values of the nodes 9 and 6 can now be improved as well. So these are the steps that happen behind the scenes in an implementation of Prim's algorithm. In each iteration, you take the current connected component, expand it by selecting the edge to the node with the smallest distance value, and potentially update the distances to all nodes reachable from the newly added nodes. Typically, all unvisited nodes are stored in a so-called priority queue, along with their current distances. A priority queue has the advantage that the node with the minimal distance can be extracted very efficiently. As the component grows, distances are updated, and in every iteration the node with the smallest distance is extracted from the queue. Note that for the update step it is important to remember how the distance was updated. that is, from which nodes the updated node was reached. We will store this information using a parent list, as you will see in a moment. The implementation of Prim's algorithm may appear a bit complicated at first, but it's actually very easy. Note that I rewrote the Python code here in such a way that it matches most of the pseudocodes found in the literature on this topic. To make things easier to understand, I will apply the algorithm to the following graph using the node 4 as starting node and explain each line of code along the way. The input parameters are once again the set of nodes, the set of weighted edges E, and a starting node R. The first step within the algorithm is to create an adjacency list using the set of nodes and edges. In this case, the adjacency list looks like this. Furthermore, we also create a priority queue here, though this will become important in just a moment. We store the number of nodes in a variable called numNodes, and we initialize a parent list where each entry is set to -1. This means that at the beginning no node has a parent. The parent list allows us to keep track of where each node was reached from when its distance was last updated. And then we set the previously explained distance for every node to infinity using a list of distances. So by now we've simply created an adjacency list, assigned every node a distance of infinity, and made sure that no node has a parent. For each node I, we put the tuple consisting of its distance and the node index I into the queue. Additionally, we create here a new list called inQueue, where every entry is initially set to true since all nodes of the graph are contained in the queue at the beginning. Now we set the distance of the starting node R to 0. Since the node R is contained in the priority queue, we update its distance using a function called decreaseKey. More specifically, the function decreaseKey takes the Q, the new distance of the node R, and the node R as input, and updates the distance value of R inside the queue. In this example, I apply insertion sort after every distance update, so that the queue remains sorted, and q.get simply returns the tuple at the front of the list. Now we are approaching the main loop of the implementation. While the queue is not empty, we extract the node v along with its distance current dist from the queue using q.get. As explained before, q.get returns always the node with the smallest distance from the queue. This is very crucial. As the node v has been extracted from the queue, it is no longer contained in the queue, and thus we set inQueue of v to false. Now what is the idea behind Prim's algorithm? We currently have a connected component consisting of a single node, the node 4. Our goal is to expand this connected component by selecting the edge with the smallest weight that connects it to a node outside of that component. To do this, we look at all neighbor nodes of node 4, that is node 0 with weight 3, node 5 with weight 5, node 8 with weight 25, and node 9 with weight 4. In general, only those nodes that are still in the queue, so only nodes that are not yet part of the connected component are considered, and are collected in the list valid neighbors. Step by step we go now through each node u with edge weight from valid neighbors and check whether selecting the edge to u would provide a benefit. In other words, we check whether the current edge offers a shorter connection to u than we've seen so far. If that's the case, we update the distance of u to the new weight and set the parent of u to v, since that's the node from which we are reaching it. Finally, we apply decreaseKey to update this change in the queue. Basically, the distances and parents of all neighboring nodes of v will eventually be updated. The for loop will terminate once all valid neighbors have been processed. Once all valid neighbors have been processed, we reach the point where the main logic of the algorithm becomes clear. We select the node that offers the smallest distance value to the current component. This is exactly the node returned next from the priority queue. Note that all nodes in the animation that are no longer in the priority queue are colored green. Furthermore, if there is a parent relation between two green nodes, it means that the edge between them will be part of the minimum spanning tree at the end. This is because a node's parent can only be updated while it is still in the queue. Also note that in each iteration of the while loop we extract one element from the queue, and since the queue contains only a finite number of elements, the loop will terminate. For the sake of completeness, I will let the animation finish now. See you in the next video.